Good morning, everybody. First, I want to thank all assistants. I hope you find the presentation interesting. Also, thanks to AFM team that have helped me with the organization of this webinar. Let me introduce myself first. My name is Carlos Galleguillos. I work as a senior engineer in the additive manufacturing unit at CATEC. I've been working with these technologies for 7 years approximately. Also, as additive manufacturing unit is part of CATEC Material and Process Division, I've been working with non-destructive testing since 2012, more or less.
Sorry, Carlos.
Yes.
Sorry for interrupt you. We can't see your screen, the presentation.
You cannot see?
Yeah.
So as I was saying, sorry about that. I've been working also in non-destructive testing since 2012 with, for instance, techniques like infrared thermography, laser xerography, metrology techniques, digital radiography, and computer tomography. So I'm the speaker today, but also with me, in mute, but they are there as you have heard him. Antonio Perignan, that is the head of the unit, and Javier Santalaya also, that is part of the additive manufacturing unit and also a computer tomography inspector. So before starting, let me give you a brief introduction of the ADDITOOL project, which is the main reason we are here today. ADDITOOL is an Interreg project with a partnership between University and Technological Center from France, Portugal, and Spain. On the right, the image on the right, you can see that we are 9 partners from France, Estia and ENIT, from Portugal, Politécnico de Leiria and Cefamol, and from Spain, the UPV, University of Basque Country, ADIMAT, SEIT, LORTEC, and CATEC. Okay. The main goal of this project is to develop additive manufacturing in the tooling sector. To do so, we have performed a market study, a technological demonstration through 5 pilots, and you can see some image down here. Researchers' mobility between centers and universities, and some courses and webinar in order to share our knowledge. This project will finish in February, is close to finish in February 2023. The final event will be in San Sebastian. In case of any of you can join us, it will be a great pleasure. Even more, in the ADDITOOL website, down here, is written down here, you could find all the information of the project and information of different pilots. So this is the index of the presentation. First, I will give you a short introduction of CATEC, who we are and where we are. Secondly, I will use only one slide to talk about most common additive manufacturing technologies, metal additive manufacturing technologies. Then I will give an overview of most common AM defects and non-destructive techniques. And finally, some conclusions before the round of questions. So CATEC is a research center for advanced technologies located in Seville, the south of Spain, mainly related with the aerospace sector. Although, of course, we also give our support to other industries, such as automotive, energy, oil and gas, defense, and many others. Our main goal is to develop technological knowledge and to transfer this knowledge to the industry, to the companies. We are focusing TRL from 3 to 8, which means from concept and development to qualified components and systems. There are 6 units in CATEC working in research axis as unmanned vehicles, drones, robotics and automation, and materials and processes. As I said before, I work in the additive manufacturing unit, but with a close collaboration with the testing and advanced unit where the NDT are used. Regarding additive manufacturing development, we use the next equipment presented in CATEC, a computer tomography system, microfocus, and up to 225 kilovolts, 3 laser-powered bed fusion machines from Renishaw, and reduce built-in volume, which is this one, this small one, to develop new materials, and a direct energy deposition system feedback wire, which is a melting head mounted in a KUKA robot. As I said before, and also related with additive manufacturing, aerospace is the sector in which we have the most of our workload. In this context, here you can see some components developed for launchers as Vega, Ariane 5, or satellites as Ibarcos, Keops, Quantum, Proba 3, JUICE. If we talk about aircraft, CATEC has also developed solutions for C295, A400M, A320neo, TS2 demonstrator, and the Racer helicopter from Airbus. In some of them, highlighting in yellow, we have reached TRL from 5 to 6, which means that these brackets have been tested and validated, but not installed in an aircraft, launcher, or satellite. However, the development highlights in red are flight components, so they are flying and ready to fly. This is updated till 2020, and we're still working in flight components during 2021 and 2022. With regard to metal additive technologies, I'm not going to go deep in the definition, typology, or even advantages and disadvantages. In fact, I strongly recommend the webinar presented by our college from the University of Basque Country, name you can see down here, boosting digitalization and die mold sector through metal additive manufacturing. You will find it, in my opinion, really interesting in case you are looking for more technical detail. You can find it, for example, in YouTube, okay? Or even in the ADDITOOL website. Either way, what I would like to remark in this slide is that both PBF and DED are the additive manufacturing most developed technologies. So inspection and manufacturing procedures, defects typology, customer specification, etc., are mainly related with these 2 processes. So let's go with the defects. Most common additive manufacturing defects are presented in these slides. There are many ways to classify them regarding shape, origin, process defect, material defect, and so on. I have followed the ASTM standard written down here. If you can note it, I strongly recommend, if you have access to the ASTM standards, to download it. as it gives you a wide overview of the NDT and additive manufacturing defects. So in the next slices, we will have an overview of voids, lack of fusion and gas pores, cracking and delamination, layer and cross-layer defects, trapped powder, inclusions, poor dimensional accuracy, residual stress, and volume. So voids is a general term for both irregular and spherical shaped cavities. So when we talk about voids, we are including gas pores and lack of fusion. So gas pores, you can see some images in here, on the top, could be produced by trapped gas in particles, for instance, gas in the powder itself, but also could be produced by high energy, so that gives you spherical cavities. And on the bottom, you can see some images of lack of fusion that are normally produced by inefficient melting regime that gives you some elongated cavities. Other typical defects presented in additive manufacturing are cracking and delamination. These anomalies could be caused by high energy density and fast cooling rates. These thermal gradients cause residual stress, and that could finally induce cracks and delamination. You can see here, this is a computer tomography cross-section with a crack in here, some micrograph images with micro cracks, and some delamination that you could see at naked eye. Layer and cross-layer are defects that propagate within a layer or along the built-in direction. This defectology could be lack of fusion, cumulated porosity, as you can see in this micrograph. It is cumulated porosity in a layer, and delamination, cracks. This is, for example, a digital radiography image with it. You can see a lack of fusion produced by a start-stop in the machine. Trapped power is a defect produced when melted powder is trapped in inner cavities of the part. As you can see here, this is also CT cross-section, high resolution CT, where you can see the shape of the powder within the melted part. This is another cross-section of the computer tomography when you can see some cavities without trapped power, more darker, and with trapped power. Inclusions are normally caused by cross-contamination with other materials, or even can be produced as an interaction with contaminants in the building chamber. Here you can see other examples in the image. This is aluminum powder for glass powder bed fusion with some white spots that are inclusion of stainless steel. This is a solid material with an inclusion close to the border. And this is a digital radiography image where you can see here an inclusion and also some lack of fusion in the material. So talking about dimensional accuracy, what poor dimensional accuracy could be obtained by different causes, such as residual stress, shrinking, bad approach in support structure, etc. In the image on the right, which is a CT, a computer tomography cross-section again, you can observe the deviation related with the shrinking the part. And what does it mean? The manufactured layer height is not exactly the same height of the nominal value. So for large component, this deviation is cumulated, obtaining, for example, between 0.5 to 1 millimeters deviation in the height of the component. As you can see here, between the nominal, that is the red line, and the top view of the component, that is the gray, you have a deviation on the top. Okay, this deviation is that you obtain here is an over thickness for the machining process. Okay, other example is the image on the left. This is also a CT scan while the part is still on the plate before extracting the supports. We detect deviation again from 0.5 to 1 millimeters between interfaces that are these legs. Okay, they move to the center of the plate. And these deviation were related with the expansion coefficient of the substrate, which was from an aluminum alloy. Residual stresses appear with rapid cooling of the melt pool that could produce high thermal gradient in 13 areas, causing cracks, delaminations, or separation of the built-in plate, as you can observe on this image. Moreover, and it's also important, residual stress can reduce the structural effectiveness. That is why it's so important to perform thermal treatment. For instance, stress relief. And finally, boiling is a phenomenon that is produced when lack of wetting appears between the molten input material and the underlying substrate. It could be caused by high scan speed, for example, or even by a high level of oxygen. The boiling effect can produce voids in PBF components. So these are the most commonly non-destructive techniques used in additive manufacturing: part inspection, ultrasonic testing, as you can see there, ultrasonic testing, infrared thermography, penetrant testing, process compensate resonance testing, metrology, eddy current testing, radiographic testing, computer tomography, and on the other hand, some of the entities are not commonly used when inspecting AM components. So I'm not going to cover them on this presentation. Okay. I'm talking about acoustic emission, leak testing, neutron radiography, magnetic particle testing, and visual testing. I'm not going to cover visual testing, although it's often used for everybody to inspect at least qualitative inspection in the additive manufacturing components. So let's start with ultrasonic testing. In ultrasonic testing, an inspector will use a probe or some kind of traducer to send sound waves. You can see in the schematic view here. As I said, to send sound waves through the material they want to test. If there are not defects in the material, the sound waves will pass through. But if the sound wave hit a defect, they will bounce off and indicate its presence. Okay, as you can see, for example, in this echo, crack echo. Okay, with this technique, it is possible to detect porosity, lack of fusion, layer separation, cracking, inclusion. As main advantage, it is a quick inspection. But on the other hand, one of the main limitations when inspecting AM components is that it strongly depends on the surface roughness. So you may consider the inspection where the surface is machined. Infrared thermography uses a sensitive camera that is able to detect the amount of infrared energy released by the object. When hitting the component, the reflected thermal wave will be different with or without effect. As you can see here, the heating source, the reflected thermal wave, and when you have a defect, the response change with the defect. So main advantage are that is a quick observation of large surface, and that is a non-contact technique. On the other hand, main limitation is that requires a direct view of the sample. Detection depends on the surface orientation and only is able to detect surface and subsurface defects. But also, on the other hand, this technique is a powerful tool in process monitoring. Penetrant testing basically works applying a penetrant agent into the surface, and after removing the excess, a developer, typically a dry powder, is then applied to the surface to draw the penetrant in the crack and produce a surface indication. This technique is only used to detect surface defects, but as main advantage is that it's inexpensive. On the other hand, surface condition affects the performance of the inspection, and also the discontinuity depth is not provided. You can see here, for example, an image with an indication, a typical indication of penetrant testing. Process compensate resonance testing works with the resonance frequency of the material. So you first need to excite the part at its resonance frequency and compare with a nominal value. If a shift in the signal is produced, it means that you have a discontinuity affecting the structural integrity. So as main advantage, it is a whole body test. It's really quick, approximately two minutes. And even you can generate a pass-fail produce process easily. On the other hand, the anomaly need to affect the structural integrity, and it's not useful to identify specific anomalies. In any case, this technique is capable to detect a wide range of defects, as you can see down here. Voids, layer flaws, cross layer, and melted material, lack fusion, and so on. Regarding metrological inspection, there are different techniques. For example, laser scanning. On the left, project a laser line and capture the reflection. A structured light scanning employ a light projector to project a node pattern of light, and photogrammetry use high-resolution cameras and markers, and using triangulation, it's possible to locate that surface point. The idea of this technique is to create a 3D point cloud or continuous mesh in case of the laser and structural light scanning, or discrete information in case of photogrammetry. These techniques are mainly used to analyze geometrical deviation, so that is the main limitation regarding defect detection. But in any case, are a good option to geometrical analysis of complex geometries. So eddy current, how does eddy current works? Well, the idea is to produce a magnetic field around the coil, these blue lines, which is called primary field. And when it's close to another conductor, it induces an eddy current in the other material, which is these red lines. This eddy current develops another magnetic field, the secondary field, that affects the primary. And any change in the material, for instance, defects, will affect the magnitude of the eddy current. So you will see the deviation in the field. Okay. It has many advantages, but in my opinion, main limitation are that only detect surface and subsurface discontinuities. Although is suitable for automatic inspection, for instance, and has rapid measurements capability. Okay, in radiographic inspection, the part is placed between the radiation source and a film or a detector, digital detector. Once the radiation is start, the part will be absorbing some radiation depending on its material density and thickness. Thinner or less dense material, for instance, a defect or a void, will allow more radiation to pass through the specimen. So you will see as lack of, let's say, lack of material, okay, the defect. There are a wide variety of equipment, sources and detectors. This is one of the most usage techniques when detecting internal flows in big components. Other big advantage is that in case of digital radiography, image filtering could be applied to improve defect recognition. Although it's a not contact technique, excessive roughness could give you false positive, for instance, in parts manufacturing with GED. And again, it is possible to detect almost all types of additive manufacturing flows. As you can see here. So computer tomography. Computer tomography uses the same physical principles that radiography testing, but this time you need several radiographic images to generate the CT dataset. Okay, as you can see on the image, the part is placed on a rotation platform. You shot with X-ray. This is the X-ray tube, and the X-ray images are generated in the digital detector. When you are obtaining between 800 and 2,000 projections, you compute that images and you obtain the CT, the computer tomography dataset. So you are able to see all the inner and outer features. This technique generates a 3D representation of the inspected component. So it's also used for dimensional analysis, even for really complex geometries. As you can see, this lattice structure in here, and inner features, inner cavities. This technique is very powerful detecting inner defects. As you can see here, maybe, I don't know if you can see here some pores, some voids. Also is powerful to detect inclusions, cracks, etc. Well, CT inspection is also a very powerful technique during material characterization. For instance, let's think that we are developing a new material or even a known material, but with new parameters for increasing productivity, for example. With PBF, you can manufacture several cubes in just one substrate or plate with different parameters, and only with between 1 till 3 inspections, computed tomography inspections, you can obtain best approach in terms of densification in your design of experiment. As you can see here, this is an example with a new material with porosity around 7%, and you can inspect, for example, a bar with different parameters, and you can choose your first approach to obtain good densification. So it's a really quick technique to improve your process in terms of densification. Other usage of CT is to inspect PBF raw material, powder, metallic powder, looking for inclusions, as I showed you before. These are 2 inclusions, or even high resolution inspection to analyze powder. As you can see in here, we perform this type of inspection for looking for or seeking the morphology and clustering, and also to analyze the powder degradation during the usage of the powder. So this technique is also capable to detect almost all the AM defects, and what is more, to show 3D information about the location and shape of the defect. That is why it's a powerful tool during process development. Also, it's the only technique capable to inspect particular structure, and roughness has no influence in the results. On the other hand, one big limitation is the maximum size of the part to be inspected. For that reason, it's not the best option when inspecting parts manufactured by DED, and also is more expensive and slower than other techniques. Here, I just put an image of the relationship between resolution and penetration. So if you have, for example, an equipment that can reach 225 kilovolts, you can penetrate 80 millimeters of steel, for example, with a resolution of 50, for example. Okay, so as more power that you have in your equipment, your spot site, that is where the X-ray are generated, is bigger, and you lose resolution. Okay. Okay. This table shows the AM defects detectability depends on the non-destructive technique. For instance, penetrant testing and eddy current are good techniques to detect the defect surface, because you can see on here in these remarks applicable if on surface. Okay, for example. The process compensate resonance testing is also a good option, but as you can see, the most promising inspection method is computer tomography, that is over there. Decoloration, for example, is observable by naked eye, so it's not quite important. It's not an internal defect. Residual stress is only not detectable, but that's why it's important to make heat treatments. This is one of the reasons that CT is being considered as preferable method when inspecting additive manufacturing space hardware. So let me present an example. These are some standards and specifications for producing aerospace components, ECCS, from the European Space Agency, PMP from Airbus Defence and Space, and AMS from Airbus Commercial. All of them consider CT inspection as the main method when inspecting critical components. You can see here, for example. The customer have to define the safety classification of the part according to functionality and requirements and other requirements. And then the acceptance criteria in terms of gas porosity, inclusion, lack of fusion, etc., is met. And when inspecting a flight components by ACT, you need to use some image quality indicators together with the component, that is this kind of parts, small parts. It has standardized defects on it, and it is used to assure detectability. Let's put an example. This is a Stalmalloy bracket manufactured by Laser Powder Bed Fusion. It is a flight component, and it is installed in the JUICE satellite, which will travel to the Jupiter icy moon. It's part of the secondary structure, and the acceptance criteria was set in 500 microns. And in case of section lower than 25 millimeters, the acceptance criteria was set on 300 microns. As you can see here on the right, that this is a inspection of the whole component with a resolution to meet this 500 microns defect detectability. This is a cross section of the IQI, where you can see that black spot, that is the 5 microns defect. And then there were, as I said before, there were more critical areas or regions of the component that had to be inspected in high resolution. So as you can see here, for instance, the 200 microns defect, it was observable. So it's an indicator that your inspection was performed correctly. So finally, some conclusions. Non-destructive inspection are commonly used at the final stage of the manufacturing process, although it's a good practice to include this testing in intermediate stages, saving cost, for example. Although your process is controlled and closed, aleatory AM defects could appear. It's something that you have to take into account. That is why the non-destructive testing they are still important at the end of the process before delivering the part. Computed tomography is one of the best options in PBF parts, with a combination of surface defect detection technique as penetrant testing, for instance, but take into account that you need a good surface quality. For example, in interface that they are normally machined. Non-destructive examination of final components produced by DED is still under discussion, because CT is not a good option when inspecting big parts. Eddy current, ultrasounds, ultrasonic inspection, penetrant testing, and radiography testing need good surface quality. Most of them, at least the three first, eddy current, ultrasonic, and penetrant. Process compensated resonance testing could be a good option if mechanical integrity is under study, but always taking into account their limitation. That is a whole body test. You won't acquire anomaly identification, and it is sensitive to a process variation. For instance, the weight, same component with two different weight could give you bad results. That is why, and in my opinion, it is important to spend time and money in the process monitoring in DED, and maybe to have the digital radiography in mind to inspect big components, and maybe computed tomography for medium small components. Okay, these are I leave here some reference that I have used, and that's it. Thank you for your attention. So in that we can open some questions if you are interested. We are here to help. Is there any question?
Thank you, Carlos, for the very clear presentation. Maybe you can write in the chat your email, and anybody who is interested or have any doubt, maybe could ask you directly by email or whatever.
Yeah, for sure. I will be very happy to have. There you go. Also, I'm going to share the link for the final meeting. If there are not questions, I will leave 1 minute more, and if not, of course, you can directly write me an email. I think that there is a question from Inigo Tercero. It has a hand raised. Can you write it on the chat?
Yeah, I can write, or I can just ask you, what technique will you use during the process? I mean, some parts are really long to process and will be interested while you are processing the part without stopping the machine. We were able to see what we are processing in real time, at least.
Yeah.
So,
yeah.
Do you think is any machine, any equipment available, any approach at least?
Yeah, in my opinion, for example, the techniques that use X-ray are totally discarded during the process, digital radiography and computed tomography. Also contact inspection as ultrasounds, the current, and so on, penetrant testing. I think that I will go for infrared thermography, but always taking into account what kind of defects that give me that thermal variation. So it's something that you have to study at first, but then as a monitoring process, the infrared thermography is quite good. And also maybe in terms of the position, for example, or for instance, GEG, I will maybe use also a metrological, maybe a laser scanner or something like that, to see the height that we are deposition, or something like that. They are really quite fast techniques that can give you information during the process.
Okay.
So I'm really glad and thank you for your all to assist this webinar. I hope you enjoy a little bit this hour, and of course I'm available if you have further question or if you need any specific meeting. You have my contact in the chat. Okay. So thank you for assisting. Thank you, Antonio and Javi, for your support. And if I don't talk to you, have a nice Christmas and hope you enjoy your vacations. Bye.
Bye bye.